Well, finally, it's Friday afternoon. I've spent the last 2 or 3 days working on this lecture, believe it or not. It's hard to do. And, normally we like to do something where it's like introduce the topics, explain the background of the topics, derive some stuff, and then do an example problem, right? But this is one of the cases where I really think that we need to go through one long example and during the process of making this long example, I'll explain the stuff as I go along, right? So we'll see how it goes. It's not normally how I do things, but you got to try something new. Trying times, right? Trying times. So let's go to our slides here. So mechanical engineering 342. Notice I don't normally spell that out. Machine component design. I normally don't write that out. Weak aid, gear and arrows. Long example with explanations at each step. Christopher Michael Dressler, Doctor of Philosophy. Right. Now, I normally wouldn't write something so pretentious on the front slide, but I'm trying to make this as long as I can because it's just going to be long. We might have to break it into a few videos. All right, so what we're going to do is we're designing a gear train to drive a wood chipper with an electric motor. Now, that sounds stupid, right? But you'll see why having an electric motor driving a wood chipper kind of makes for a good problem. So we're going to use a 15 kilowatt motor. That's about 20 horsepower. It runs at 2,500 RPM. And so the way this is going to drive is, so we'll have where's the camera? Wrong side. Okay. So we're going to have the motor spinning, right? I'll do it like this. The motor spins like this, and it drives a 14-tooth pinion. And that pinion is going to drive a 17-tooth idler. And this is important to why we're going to talk about an idler in a little bit. So the pinion drives an idler. Then the idler then drives a gear, right? And the gear, I think, has 49 teeth. No, we don't know that yet. Whatever. The gear has some teeth, right? And the gear ratio is 3.5. But what's interesting about this is that the pinion drives this idler. So the idler gets driven by the pinion, but the idler also drives the gear, right? And so this is going to wind up being a 3.5 speed reduction, or a speed ratio of 3.5. All right, so anyway, back to the problem. And the module of the pinion is 5 millimeters. Speed reduction is 3.5. We said that already. And typical, landscaping equipment, wood chipper, pressure angle of 20 degrees. That's kind of standard stuff. For some steel gears, we're going to select a good face width. And so we got to start somewhere. And so I decided, well, let's try 1045 hot rolled steel because we know some properties of that. All right, so let's go from there. All right, the first thing we have to do is some power stuff, right? Well, I know that 15 kilowatts, right? That equals 15,000 Newton meters per second. Right now, that's not a very useful unit for me, really, because I'd rather work in millimeters, right? So it could also equal 15 million, ridiculous, per second, right? Why would I convert it to, instead of 15 kilowatts, 15 million Newton millimeters per second? Because this is convenient for megapascals, right? So I know, and again, as I mentioned in a previous lecture, the one that kind of sucks. It's actually, I rewatched it. It's not that bad, but it's not that good either. That I know that power, W dot equals the torque times the speed, right? That's omega, torque times omega. W dot equals torque times omega. And for the units to work out here it's more convenient for me to work out in newtons and meters. So this equals, so the power, which I know is 15,000, equals torque, which I don't know, times omega. And so 2,500 revolutions per minute, that works out to be 261 radians per second. Okay, so I've got some unknown torque times Well, what's going on there? Why didn't that work? Now my stylus isn't working. Times 261. And radian is really dimensionless, right? A radian is arc length per radius. So that's dimensionless. So this works out to be my torque. Works out to be, what is it? 57.3 Newton meters. All right, so I'm still working in a relatively not a good unit system, but I know it's 50, so I'm going to put a dotted box around that because that's a pretty important intermediate step. All right, now I know that module it's in millimeters, so it's millimeters of diameter per number of teeth. So I know I've got 14 teeth, so 14 teeth times 5 millimeters per tooth. And so then I find out that the diameter of my gear, what's 14 times 5 is that 50, 70? 70 millimeters, right, which equals 0.07 meters, right? So I have not yet decided what my unit system should be, so I'm kind of mixing it up. 0.07 meters, and then so now I can figure out my F tan here, so I know that torque equals R times F tan. Now I know my torque, I know my radius, so I can get an F tan works out to be 1,637 newtons. All right, that's a pretty important intermediate step. That gets a dotted box too. All right, 1,637 newtons. All right, so that's kind of my power and some of the other stuff I get from power. All right, what's next? Force analysis. I think I actually did that. Oh, well, we better do this too. So I've got a pinion. Let's go from left to right. I've got a pinion. And the F tan there is, what is it, 1637? Right, and that drives, that drives an idler. And so if the tangential force on the pinion is resisting the motion, right, because that's driving, so that means this thing must be rotating this way. And if that's rotating that way, this must be rotating this way, right, because the gears mesh here, and so the gear teeth move downward like that, which means on here there must be a force resisting or driving the motion. Oops, that didn't go well there, so it'll go like that. So there must be an F tan there. Equals, you know what? It's got to be the same. It's got to be 1637. Right? The force on the pinion tooth has to be the same as the force on the idler tooth, right? So what the heck does this system do? Oh yeah, this is going to have a greater torque, right? Same F tan, but because it has a bigger diameter, much higher torque, right? And then this thing will drive a gear, which is even bigger. Let's see, it's rotating this way, so that means on the driving side, it's got a force resisting its motion, right? That also has to be F tan. So these guys are moving up like this, which means there must be a force this way on that gear tooth there that also has to be 1637. Whoop, erase that. Why is my eraser not working? Work, eraser. There. So this F10 also has to be 1637. And then this one is rotating, let's see, this way here. All right. So it's a little counterintuitive, unfortunately, but you got to be able to keep in mind, and we did this a long time ago when we first did your force analysis, but it's going to get more complicated now. Which way is it rotating and which way is the force? If it's driving, I'm rotating this way, but I'm pushing and resisting the motion, right? So there's a torque opposed by a torque. On the idler, it's got two forces, a driving force and a driven force, and those two cancel out to put it in torsional balance. And then finally on the gear, right, the force is causing the motion, right? So that's tricky. We got to keep that in mind. So that's our force analysis, and I think we're good there. So let's go back to here. What happened here? Oh boy, this is not good. Gear analysis. These are all my pages. Yeah, so we did that page, power calculations, force analysis, good there. All right, and so here, I think this is just a fantastic image. Just a fantastic image. So if I'm trying to draw, analyze this, I've got two big problems, right? I've got a big bending problem here. I've got a big bending problem here. So bending there and there. I can see the bending, photoelastic image, right? Maybe some of you did this in your high school science class where you look at polarized light coming through a ruler and you twist it. And then finally I've got, look at that, all that stuff there, contact stress. Contact stress right there. So these are the two places I have to look at, right? First we're going to look at the bending, and then we're going to look at the contact stresses, all right? So the Lewis equation, first pass, right, is the Lewis equation. So I don't want you to just look at this equation here and just say, I don't know, what does that stuff mean, right? Well, I'm trying to figure out the bending stress. And so the bigger the tangential force is, right, it makes sense that the bending stress goes up, right? More force, more bending stress, that's fine. What about B, right? B is face width, right? Well, the wider the gear is, the wider the gear teeth are, the more material is there to resist the bending, and so the lower the stress is, right? So that makes sense. Larger face width, lower stress. What about M, the module? Does that make sense? Should that be in the denominator? Okay, here is one of my favorite pictures, the actual size, right? And of course, it's not the actual size because I have no idea what size your screen is. But of different diametral pitches, right? So diametral pitches is n per inch, or 1/inch, whereas module is the inverse of that, right? Millimeters per tooth. So here, as I get a smaller number so if I go from 6 to 8, no, what is that? From 6, 8, 7, 6, 5, 4. What the heck is that? Oh, that's a 9, that's why. So as my diametral pitch gets bigger, my teeth get smaller, which means that for module, as the module gets bigger, the teeth get bigger. So does that make sense? Sure. As my module gets bigger, the teeth get bigger, which reduces the stress. Okay, that makes sense. Finally, we've got this thing called the Lewis form factor, right? Y is the Lewis form factor. Let's see if I can fit that on there. Darn it. Palm cancellation, my ass. Y equals Lewis form factor, okay. Well, I guess that's written down here, Lewis form factor. So let's see, I got to go say the number of teeth, and I've got, let's say on my pinion, just for kicks, I've got 14 teeth, so I'm here. So I go up to, let's see, what is this? Oh, that's the different angles, all right, so I got to go to this one here. So I go up to here, and I say, okay, so my Lewis form factor is, I don't know, Y is approximately, let's call it 0.27, what did I use for, yeah, 0.27. Right, because the geometry of these involute teeth is so complex, we couldn't calculate that, right? So it's all tabulated for us in this plot. So y is 0.27. And so we say sigma equals, let's see, f tan, we got that figured out. Modulus 5, that's fine. Y is 0.27. B, what's our face width? We don't have a good face width yet, right? Well, in general, we want gears to be, we want the face width B to be between 9M and 14M, right? We don't want gears that look like pancakes, nor do we want gears that look like hot dogs. We want gears that are a nice jelly donut, like a Bismarck, custard-filled Bismarck. Oh, delicious. So we want it to be somewhere between 9 and 14 modules. So just for kicks, I'm going to pick 12M, right, which means it's 60 millimeters wide. So if I plug all that stuff in there, I get a bending stress of 20.2 megapascals. Right, do the units work out? Sure, that's in newtons. B is in millimeters, face width of 60 millimeters. M is in millimeters. Okay, so yeah, newtons per millimeter squared, megapascals, 20.2. Sigma, a bending stress of 20.2 megapascals. Does that work? And I don't know. I mean, I don't really have a good feel for that. So let's take a look at some steels. I decided on 1045. And so it's kind of loaded in fatigue, right? So I don't know, yielding, 414 megapascals. Wow. Ultimate half of that, for the endurance. So yielding is 414, so 20 is not even close. Ultimate, so if I consider this a reverse stress or a fatigue loading, so half of that is on the order of 320-ish. Holy cow, right? So 20 megapascals versus 320, it seems like I've got a ridiculous safety factor here, right? So let's, someone asked just a fantastic question in the lecture the other day, the drop-in lecture. They said, well, is the Lewis, different books will say, hey, try this fatigue technique, use this factor for this, but use this factor for this, blah, blah, blah. Different books give you different stuff. And then someone has said, well, it's the same deal. Lewis is just one of many methods, and some methods are better than others. No, Lewis is a first pass. Lewis just gives us a very, very simple bending stress that we can use to get a rough ballpark, but as we'll see shortly, it's not even a good rough ballpark. So let's move on to a more refined model, the AGMA.